Let's commence. All right. Here is the story. You have a quiz, I guess, this week, right? Tomorrow it starts. So I'm sympathetic to this, in the sense that I know it's on chapter 15. However, I have already discussed chapter 15 and must go on with chapter 16. So there are these two opposing points of view. And since I'm at your service as always, I have to be guided by you as to which point of view I should emphasize. So put it this way. Does anyone have questions about anything in chapter 15 that they'd like to go over? Okay.
How do you tell when to use a substitution? Are they just going to say use this substitution, or are they going to have to look at the logic and be like, oh, using this substitution?
All right. So the question is, how can you tell when to use a substitution in an integral? And I presume you mean with the Jacobian, that sort of thing. So that's 15.7. So most of the questions that I've seen involving this sort of thing will say, using the substitution so-and-so, find this. Okay, so that's obviously the most telltale sign that you should use a substitution, is when the question tells you to and tells you what substitution to use. If it doesn't, then that's much more subtle. And there's no really good answer to this. I mean, the time that you really want to use a substitution is when you can't do it without a substitution. That's obviously the time to do it. But on the other hand, you might be able to make your life simpler if you do it. So I looked at an example last time where the region was contained within two hyperbolas and two lines. And so in this particular case, I might as well just revisit what they were. I mean, the hyperbolas were y is 1 over x, y is 4 over x, and the lines were y equals x and y equals 4x. And then, so that region looks like this. Here's y equals 1 over x. Y equals 4 over x is 4 times as big. And then y equals x. Y equals 4x. So even to set this up as an integral, as a regular double integral, forget what the integrand is, just the whole sort of f dx dy. Just to get that, you would need 3 regions. If you do, actually it doesn't, by symmetry in a sense, it's not actually symmetrical, but I suspect that in both directions you'd need 3 regions. You need, certainly, that's a region where you have this curve on top and then this curve on the bottom. Here the top curve switches, the bottom curve is the same, and then here the top curve is the same, but what am I talking about? Top curve, bottom curve. Different top curve, same bottom curve. Same top curve, different bottom curve. So you kind of need 3 x ranges to do it. So even not considering the f and what form it takes, there's some motivation for doing a change of variables that makes this into just u equals something, and u equals something, and this could be v equals something because they have the same form. So if you notice that y equals 1 over x is more like xy equals 1 and xy equals 4, suppose you call this u. Well, xy is u.
Okay.
So then this is u equals 1 and this is u equals 4. Okay? So we've made those curves simpler. And then the other one, you can write the curves as y over x goes from 1 to 4. Right? Y equals 4x or y equals x. And so call that v. And that's a decent substitution in this problem. And that will change the region in xy coordinates to uv going from 1 to 4, which is just a square. Now, the problem is, so it's made the region simpler. So this is tricky. You need 3 integrals, but in the du dv, you have just 1 to 4 in both cases. But you'll have a Jacobian of the transformation in there as well. Now, then you have to look at the f and the j, and maybe this new integral, although it has an easy region, maybe you can't do that either. Now, the substitution that was actually given to you in the problem, so the problem said use a substitution, turns out to have been u is root xy and v is root y over x. And the interesting thing about it is, okay, well, if y over x goes between 1 and 4 and is positive, then the square root goes between 1 and 2. So the region just goes from 1 to 2 instead. It's not any better of a substitution intrinsically. However, the integrand involved root, as I recall, it was something like root y over x plus root xy. I think that's what it was. So then that makes more sense to do it. But presumably the other substitution would have worked just fine as well. This u equals xy and v equals y over x. So I'm just trying to give you some general ideas. If the region is messy but can be transformed into something nice by a substitution that's clever, then by all means make that substitution. If the integrand also helps, then that's even more evidence to do it. Okay?
These kind of substitutions?
Okay, the quiz is on chapter 15, which means double integrals, triple integrals, polar, that's for double, and then spherical, cylindrical coordinates for triple integrals, as well as Jacobians. I'm sorry? Yeah, and then, of course, there's the centers of mass, moments, inertia, sort of, as well as areas, volumes, average values. Those are all just applications of these integrals. But that's what the quiz is. Anything in chapter 15 is fair game.
Spherical, what is
Spherical and cylindrical coordinates.
Those are for just triple integrals.
Yeah. And polar is for double integrals.
All of this is in chapter 15?
Yeah, look in the book. Open the book. Look at chapter 15, and you will see what the syllabus for the quiz is. All right? For those of you who came in a little later, the deal is, and there's no late, there's only later, earlier. You can't be late to these sessions. Come and go as you please. So for those of you who weren't here right at the beginning, I'm going to do 16, chapter 16, but because you have a quiz, I'm throwing the floor open to any questions about 15 that you might have. And when we finish those, we'll move on. So the first question was, how do you know when to substitute? Obviously, if the question says, find a substitution for this integral and use the Jacobian, etc., then you know what you're supposed to do. But occasionally, you might have to do a substitution. And I was just trying to say that unlike a single variable problem where the substitution is necessary to even do the integral, here the substitution might be necessary to get the region right, forgetting even about the integrand. So that's another consideration that comes up. Any other questions about chapter 15 before I go on? Of course, if you change your mind, you can ask me later on as well. But, you know, quiz is starting tomorrow. You know, anything on your mind? Specific problems? Homework problems you couldn't do? Previous quiz problems you've looked at? Nothing else? Haven't started studying yet. Okay.
I have one question from the homework.
Okay.
Question number 24 it was, I think. Where is the sheet you just showed me? I'll look for it and I'll get back to you. Is it okay?
Well, will it take very long? Because once I start on 16, it will probably be...
Okay, this question. Where is this week's homework? Okay,
15.
15.7, 24.
Okay. So I can look here, or I have a copy over there, but this... Ah, the cylindrical shell one, right, okay. Some people asked me this last time, and it's a... Okay, so this is the problem about showing that the method of cylindrical shells works, okay? So I'll do something about it very quickly, but I regard this as a very unlikely quiz question, because it's just too hard to grade, frankly. But anyway, it's an interesting little problem, so here goes. The question is to show that cylindrical shells works. Now, I'll tell you what cylindrical shells is. It goes something like this, and this is from Math 104. So you have some function y equals f of x, and a region between a and b, say, to the right of the y-axis. And you want to revolve this around the y-axis to get some sort of solid, which is going to have a hole in it unless a is 0. And anyway, so this top of the bottom of the solid's just a ring, but the top of this solid's going to be like a ring, but with a with a peak in it, a bump in it. So this is the sort of solid here. And the formula for the volume is V is the integral of 2 pi x y dx, which actually, since y is f of x, looks like 2 pi x f of x dx. And you're asked to prove that using cylindrical coordinates, basically. So the first thing I'm going to do is change this to the z-axis. I'm going to consider this to be the z-axis. This can still be the x-axis, and then everything is symmetric about the z-axis. Okay, so now I'm going to try to use a triple integral and reduce it to a single integral in this special case. So in polar coordinates, or rather cylindrical coordinates, I pick some arbitrary point in this region. So the base shadow is this ring down here. This is the annulus. So I'm going to pick a point here. And I'm going to ask, how high does this z ray go before I hit the top of the thing? Okay, well, let's consider the points that we're at. I'm going to say the point is r comma theta. Now, the thing is, the theta doesn't even matter. The theta does not matter. Only what matters is the r, because the whole situation is completely radially symmetric about the z-axis. So wherever your point is, the height of z only depends on r. And if you think about this point being on the x-axis, if there's a point on the x-axis with x equals r, so that's just the radius along the x-axis, not even including the y-axis, the height is f of x, or f of r in this case. So I'm claiming that the height equals f of r, where r is the cylindrical coordinate parameter. And it's true no matter what theta is, because the whole thing is revolved, as I said. So basically, as a triple and the highest z is f of r. And this is going to be, the integrand is 1 for a volume, dz r dr d theta. That's always the integrand. You need the r as the Jacobian, basically, for cylindrical coordinates. Now, what's the range of r? Well, the first radius is a, and the last radius is b. And how about theta? Well, it's the whole way around. So theta goes from 0 to 2 pi. So that's the volume as a triple integral. So step 1 is to come up with this and understand what it means. And step 2 is to actually reduce it to a single integral. So we need to reduce it to this. So let's do the z integral and see what happens. Get 0 to 2 pi, integral from a to b. The z integral, the integral of 1 is just z. So this will be f of r minus 0. So just get f of r times r d theta. Now look at this quantity. It doesn't depend on theta. A and b are constant, so it doesn't depend on theta. You can actually pull it out of the integral and just do the theta integral and get a 2 pi. And now all that's left is to realize, well, r is just a dummy variable, and we can change it to x. We can change it to any letter you like, and not confused with the other x. It just, and this becomes 2 pi x f of x dx, which is just the formula. So that's it. You turn a triple integral into a single integral. You can't do the single integral because you don't know what f is. But at least you don't have to deal with 3. Okay? Any questions about that? It's like a extra little hard, more theoretical example. But I mean, I'm not saying it couldn't be on a quiz, but it's pretty unlikely. How do I get the height equals f of r? Well, if I was just along the x-axis, then the height would be f of x. 0 to f of x. Now, if you're on the x-axis, then the x-coordinate is also the r. It's the distance from the origin. So at least when you're on the positive x-axis, it's a height of f of r. And now, because of the way it's revolved around the z-axis, then it doesn't matter where you are, you're always at the same height around that circle. And so if you're at r, you're at height f of r, the top. Okay, so basically, at this point, you have a ring of the same height. Okay, so regardless of theta, you have that height. So, of course, this only applies for solids that are formed by revolving a region like this. But beautifully, you don't actually have to use triple integrals to do it. You can use single integrals, which is why we do it in Math 104. But for more general solids, you can't do this, and for triple integrals that don't just have a 1 there, you certainly can't do this. For volumes, you have a 1. Are there any other questions before I go on to 16? Okay. So 16 is about different sorts of integrals altogether. We're going to do line integrals and surface integrals. Surface integrals not till next time. By the way, I might as well announce there is a session next week, but that's the last one until January. I'm not doing one in the last week because I will be in Australia. It's a good excuse. I guess I could do a video and send it, but there you go. However, I will be doing 4 sessions during the reading period in January, which will be a complete review of everything after the midterm, plus plenty of Q&A time. Okay, so that will more than make up, I feel, for the missing session. Anyway, my plan is to do as much of 16.1, 2, 3, and 4 as possible. So that might go a little bit ahead again, and that way next week I can do the rest of the course and then actually cover the whole thing, even if I end up doing a bit of a preview. All right, so 16.1 is what I'm going to be running again. Sweet. Okay, so the first new type of integral that I'm going to talk about is a line integral. Okay, we've done double integrals, triple integrals, now back to single integrals, but not quite the same as a standard single integral in one variable. So let's see what we're up against here. I have some vector field. So I need to talk about what a vector field is. Actually, no, I don't even, I'm getting ahead of myself. I have a scalar field. So I have a function. It's a real valued function of 3 variables. Of course, you could do this in 2 variables as well. But let's just do it in 3. So think of that as a temperature at each point in space. I write F, it could be T. So at every point in space, you have a different value of F. All right. What I want to do is take some path in space and call that C. So this could be the path of a spaceship as it navigates around. Or if it's in the plane, it could be an ant walking around. Something like that. So this is some curve, and I'm going to assume the curve is reasonably smooth. I don't want it to be too jagged. It's allowed to have an occasional corner. So it could be what's called piecewise smooth, meaning that there's a finite number of pieces where it is smooth, and then it's still continuous. It's just joined up. So that allows me to have paths that are squares and not worry too much about it not being smooth at the corners. It's allowed to have a few corners. Okay, so what I want to do is somehow add up all the values of the F, the temperature, whatever it is, along here. I might want to be taking an average value of the temperature along this path here. So there's the temperature in space. You know, it's hotter near the sun. It's colder further away, hot near some comets or something, I don't know. The moon of Jupiter is pretty hot. It's got volcanoes, EO, whatever. So you want to navigate a spaceship through a certain path, and you want to say, what's the average temperature along the path? So it's a single integral, but it's complicated because it's not just a regular function, there's a curve involved as well. So C is this piecewise smooth curve, which I guess I'll just call nice. It's a nice curve. Most of it is smooth. Okay, and what I want to do is form this integral. There's a line integral over C, the contour, of f of x, y, z, ds. And what is ds? And you might recall when we did this sort of curve stuff a little bit, we looked at parameterizations of curves. We looked at arc lengths, and we said, okay, well, you know, we can actually measure how long each bit is by using the speed of the parameterization. And so the way I'm going to think of this integral, not compute it, but the way I'm going to understand what this means For any integral, you need to know what it means, but then you need to get practical and compute it. Let me tell you what it means, and then we'll get practical. I want to take a partition of this curve, C, and remember this is in space, although I can't really draw a curve in space, unfortunately. So here's C, and I want to chop it up into enough pieces so that F is very close to constant on each piece. The temperature could change a lot between here and here, but if the piece is small enough, then it won't change very much. And then I'm going to take the length of this piece, which is called ds. That's the length of a little piece, the arc length of a little piece. And then I multiply that by F to get the temperature times the length, and then add up all of those and then take the limit as the lengths, as this partition gets finer and finer. And that's all achieved by the integral. Okay, so that's what it is. It's a single value integral, but it doesn't look like the area of a function. The way to make it into an area of the function, is imagine the function is like different heights all around here, and then you kind of take this curve as a piece of string with the function heights just hovering above it. And remember, it's in 3 dimensions. It's really complicated. But I want to take the string and yank it out and hold it, like stretch it out and put it along the x-axis. So it unwinds like this, and whatever the heights are above it also unwind and give you an actual function, and we just want to integrate that. So it is an area, but it's sort of a bizarre area. Okay, does that make any sense? So that's why it's not a one-dimensional integral by itself, but we can turn it into a one-dimensional integral. So that's the motivation behind the thing. Now, let us look at how to actually compute such a thing. And there's a couple of different forms of it. So, the sort of standard, simple way to compute, without getting into what's called differential forms, which we'll look at in a second, looks something like this. So you have some parameterization. So you have to pick a parameterization. Of the curve. And it actually doesn't matter which one you pick, in the sense that you'll always get the same answer no matter which parameterization you pick. On the other hand, you may not actually be able to compute that if you get a bad parameterization. So there's some parameter t, and that tells you all about the curve. So at time t equals 0, we might be over here, and time t equals 1, 2, and then 3. And it tells you how to get from here to here in 3 seconds, say. So it doesn't have to be the same speed. It could actually be faster and then slower, and etc. So different parameterizations are possible. Now, given that, you can find the speed which is just the length of the velocity vector. We've seen this before when we did arc length. This exact parameter comes in so that's the speed. And what we saw is that ds, a little bit of arc length, is actually v of t dt. That is not new to us. To find the arc length, we just integrated that. So now we're going to integrate with respect to that. So this means that to work out this integral, f of x, y, z ds, you have to find the parameterization. So you find the parameterization. And then the integral goes from the first value of t to the last value of t. Or 0 to 1 or anything. And now you plug in your x of t instead. X of t, y of t, z of t. So you just plug in the x, y, and z in there. And instead of the ds, you use this v of t dt. It's exactly this. X now depends on t. You take its derivative, square it. Same with y, same with z. Add them up, take the square root. Okay? This is exactly the process of stretching this thing out. And then finding this integral. That's just a regular old integral in t. There won't be any x, y, or z anymore. There'll just be some mess in t. This introduces another mess in t. But it's all a function of t. Just a function of t. And again, for different parameterizations, this might look different. But you'll get the same answer, assuming you can compute it. It's independent of the choice of parameterization. Kind of nice, huh? So this works very well, this procedure, provided that your curve is differentiable everywhere. So this is okay if the curve's always smooth. But what if it's only piecewise smooth? So if the curve has two smooth pieces joined end to end, but a corner at the join, you cannot use this formula. Yes, the good news is you just break it up into two line integrals. And do this procedure for both. Pieces. And of course, sometimes you have more than two pieces. Similarly, for three or more pieces. So you just treat it as separate problems and add them up. Do procedure for both pieces, add up results. So in particular, if C is C1 and then C2, so that I'm thinking of the situation where you have this corner there, and this is C1 and this is C2, and the whole thing is C, then the integral of f ds over C is just the sum of f ds plus f ds. So it's the sum of the integrals over the first curve, C1, which is from here to here, and then C2. You add them both up to get the answer, and you're just going to have to parameterize them separately. So, for example, here is one from the textbook. So, let C be the line joining. Actually, this is not a two-piece example, it's just a one-piece example. So, it's the line joining 1, 2, 3 to 0, minus 1, 1. And the question is, find the line integral x plus y plus z ds. Not such a hard example. We have to follow the procedure. There's only one piece, it's just a line. I say line, I should say line segment. That's more accurate. Lines go on forever. Okay. So, according to the prescription, we need to parameterize the curve, which in this case is a line. So how do we do that? Well, this is going back to the early stuff we did right at the beginning. Second week, we looked at equations of lines and line segments. We need the vector that's the difference between these two. So let V be 0, minus 1, 1, minus 1, 2, 3, which is negative 1, negative 3, negative 2. So if we start here and add v, we get to here. So we start at the beginning, add this v, we get to the end. If you only add a fraction of v between 0 and 1, you get the points in between. You get a point in between. If you do all the fractions, you get all the points in between. So what I'm going to claim is that c can be parameterized by the vector 1, 2, 3 plus lambda, or t, let's call it t, times v for 0 less than or equal to t less than or equal to 1. Let's just do a reality check. When t is 0, you just get 1, 2, 3. When t is 1, you get 1 minus 1, which is 0, 2 minus 3, which is negative 1, 3 minus 2, which is 1. And in between, you get some points in between. So that's the parameterization I'd like to use. Now let's amalgamate this into one vector. It's going to be minus t plus 1. It's going to be minus 3t plus 2. Plus, and it's going to be minus 2t plus 3. Shame about all those minus signs, but there you go. Okay, this is x. This is y. And this is z. Now, before we go and compute this, we need to work out the speed. We need to work out the speed. Luckily, because it's a line, and we've taken a very simple parameterization. We've taken a parameterization that just goes along the line like this. We didn't do something fancy like, right? We did it uniformly. So the speed should always be the same. Let's test it. V, the velocity vector, you just differentiate with respect to t. So this is minus 1, this is minus 3, and this is minus 2. Doesn't depend on t at all. Independent of t. This is true for all t.
How did you get your t going from 0 to 1?
Okay, how did I get the t going from 0 to 1?
Yeah, how did you decide that it was 0?
Well,
That's how you were integrating.
let me show you why it works, and then you will see why I knew to do it. I know it from experience. Also, we learnt it. But again, when t is 0, you get the start point, right? You agree? When t is 1, you get the end point, right? So then the question is, what happens when t is a half? And this is where you have to actually look at the vectors. So just over here, there's the start point 1, 2, 3. And here's the vector v. And I'm saying when you add v to this, you get to the end point. So geometrically, if you add a half v, you're halfway along from the beginning to the end. If you add a quarter, you're only a quarter way along. If you add 3/4, and so you see that when you go from 0 to 1, you get the whole thing. If you go past 1, you overshoot, and if you go negative, you backtrack. And if you allow t to be anything, you get the whole line. So t 0 to 1 gives you the segment. So that's a very useful technique, because very often these curves are just lines or line segments. Okay, so this is the absolute technique. Once you've seen it, believe it. But it's good to know why you're doing it. All right, so anyway, the speed is constant. Actually, the velocity is constant, so the speed is just the magnitude of this. And that's that. This is just an application of this formula over here. So maybe, right? But you notice that I computed the v first and then took its length. Of course, this is just the length all in one. But it's kind of nice to do it this way. So moving back over here, I'm going to get 9 plus 4 is 13 plus 1 is 14. So this is root 14. All right, now we can finally come back and do this integral. Let's change it to t-land. It's a sort of substitution. The c, the contour, we've decided is parameterized for t between 0 and 1. And now we look at what x is. Well, according to this, x is minus t plus 1. And y is negative 3t plus 2. And z is negative 2t plus 3. So that takes care of the integrand. Now, I've boxed myself into a corner here, and I don't have enough room to write down what the ds part is, so I'll have to do it down here, but hopefully you can fit this in as a factor over here. I feel so bad about it, I'm going to just go to another board and rewrite it. It's not good to cramp the style or the symbols. So let's try that again, shall we? You don't have to rewrite this. You've left yourself enough room. Integral x plus y plus z ds over c is equal to. So I'm just going to have to copy it again. It's minus t plus 1. That's the x. Of course, this could have been x squared, and I would have squared this quantity. It just happens to be x in this example. Then I have minus 3t plus 2. And minus 2t plus, was it 1? 3. Okay, so that's the integrand. The ds, remember, we're going to change this to absolute value of v of t, as in the speed, dt. And we've already computed that this is root 14, independent of t. Constant speed parameterization. But in principle, this could have been a function of t. And that is going from 0 to 1. And now the thing becomes a piece of cake. We have minus 6t. Root 14 is a constant, so I'll pull it out. I have minus 6t. I have 1 plus 2 plus 3. That's the 1, 2, 3. So the integral of minus 6t is minus 3t squared. Go between 0 and 1. And this just works out as 3 root 14. Okay, so what that means is if you take this function x plus y plus z in the plane, in space. So now here's x, here's y, origin, and it's sort of getting bigger in the positive orthant or octant. And it gets smaller down here as the coordinates get negative. It's just the sum of the 3 coordinates. But we're taking a line between 1, 2, 3. So that's this point up here. And then the other point was 0, minus 1, 1. And we're adding up the values of x plus y plus z along this line. And it turns out to be 3 root 14. Now,
it's not curved like it was before. It's just a straight.
In this case, it's a line because that's the problem. The problem asks for the line. But I mean, you could ask for a curve. And then you'd have to parameterize the curve. Okay? So the point here is that if this x plus y plus z were just 1 instead of that, you would just get the length of the line. Or in this case, it's a line. But I mean, if it's a curve, you get the length of the curve. The only difference here is that we're not just getting the length of it, we're weighting it differently. We're taking the length times the value of the function at that point. So it's just a generalization. Similar analogy would be if you did a volume integral with just an integrand of 1. That just gives you the volume, a triple integral rather. With just a 1, this is a volume. But if you change the 1 to something else, it's not just a volume. You're counting mass, if you like, at different parts of this solid differently. Could even be negative. So it's not just a volume. Just like this is not just a length integral, it's a line integral because of this. Now, by the way, a line integral can also be a curve. As in, I've presented C as being a curve. It's called a line integral. But that's just a terminology question. Okay? It should really be called a curve integral. But for some reason, that's not what they call it. All right, so, question.
Is there a way of knowing whether to expect the result to be positive?
Is there a way of knowing whether to expect the result to be positive? Okay, if the integrand is always positive, then the answer had better be positive. But in this case, the integrand is not necessarily always positive. As it turns out, the integrand, if you look at it along this curve, is minus 6t plus 6. So it does always turn out to be positive for t between 0 and 1. Right, but I mean, if the integrand had all squares in it or exponentials or something, then it ought to be positive. But there's no guarantee. And in this case, this function is not always positive. It just so happens that the path is in a place where the function is always positive. Any other questions about this example?
So is the line integral maybe like a sheet going down from like where the z is down to the xy instead of, because it's not a bar?
No, it's not a sheet going down from the xy. The easiest way to visualize it is just to do a two-dimensional line integral. Okay, so I'll answer your question about how to visualize this with a two-dimensional line integral. Okay, so in that case, we're trying to we have something like this, where C is now a curve in the plane. Okay, so x, y, C might look like that. Okay, and f is a function. So what I want to do is plot the function like this. Here's x, here's y, and here's z. And I'm going to plot z equals f of xy. Okay, that's going to be some surface. Okay, now take this curve, which was over here. It's a bit of a complicated curve. Maybe I'll just do this. Okay, and I've got to do it in perspective down here, so it'll look something like this. Okay, now what I want to do is project this curve up to the surface. So actually, you do get some sort of sheet. It's like a curtain around it, but the height of the curtain depends on the height of the surface. And I'm actually going to throw away the entire rest of the surface. So this is some curvy sheet. Now stretch it out into a straight sheet. So actually just pull out the sheet and find the area.
Okay.
That's exactly what that line integral is. Now, if it's a three-dimensional line integral, you actually need a four-dimensional picture. You need the x, y, z, and you've got some curve in there, and then some fourth dimension, which none of us can visualize unless we're on some serious drugs or something, but whatever. You need a fourth dimension to display the height of the function. Right? The problem with being on the drugs is that even if you see the fourth dimension, you can't remember it when you're going to do anything useful, so don't do drugs. All right, so that would be an interesting excuse. But hey, my math lecture said it was okay because then I could understand four dimensions. Yeah. Then I get arrested. I can't do the reviews in January. So don't do that. All right. So anyway, and if you do it afterwards, then clearly not my fault because you don't need. Yeah, exactly. So right. So I don't know how you see this thing in four dimensions, but it would be the same sort of analogy. You see why you need four, right? The curve's in space, and you need another axis to represent the height of the function. Okay? If you're just doing an arc length integral, meaning there's no y plus y, but it's just a 1, then the height of this curtain is always 1. And the reason you get the length is because when you stretch it out, it's just a rectangle of height 1. And so the length of this times 1 just is the length of this. Okay? 1's good like that. All right, so that's what it is philosophically, and there's an example of how to compute it. Pick the parameterization, calculate the speed, and just plug it into the formula. Understanding that what we're doing really is computing little bits of arc length and adding up the appropriate function values multiplied by that. For double integrals, what we were thinking of is some planar object, like a flat disk or a flat piece of metal. It's having three-dimensional, no thickness, or very, very thin. For a three-dimensional thing, we were thinking of a solid object, trying to work out its center of mass. The line integral is appropriate for when you have a wire, like an object that's stretched out along a line. So imagine you had a curved piece of wire, but it doesn't have to have the same density everywhere as usual. The density can be heavier over here and lighter over here. So there's some density, delta, and I'm assuming this wire is curved in space. And at any point x, y, z on the wire, there's a certain density that tells me how heavy the wire is near there. Per unit volume, well, per unit length in this case. So then you have these first moments rather. M, y, z is, so I parameterize this. I think of the wire as being along this curve C, which again, the wire is allowed to have a small number of sharp corners, but mostly has to be smooth.
But we're doing no masses, center of mass.
Yeah, center of mass for wires,
Center of mass.
of a wire. But luckily, the formula is exactly the same as it was to get the YZ moment. So there's some YZ plane. Here's X, here's Y, here's Z, and the wire is in space. And if I want to know what is this sort of first moment of attraction down to the Z, the XY plane, the YZ plane, it has the same formula that it did. It's just that, so we multiply by X, the signed difference from the YZ plane, times the density of the wire. But this time the integral is not dA or dV, but it's ds. And similarly for mxz, and similarly for mxy, that's about the xy plane. And these are all line integrals. And then the center of mass, well, I should have mentioned, maybe squeeze this in above. I didn't even say what the actual mass is. The mass is formed by adding up all the densities along the line. And then you have these first moments. The mass is the 0th moment, actually. And then you have all of these moments. And then the center of mass is equal to myz over mxz over mxy over m. And I have the same caveat that although it looks strange, this integral here involves an x. So the x-coordinate is the one with the x. This one involves the y, and this one involves the z. It's just the notation is a little bit unfortunate, but you kind of need to have it. It's really in a moment about a plane. So it's a physical reason, and again, I don't have enough time to go into the physics of the whole thing. But this is the center of mass of the wire, and it doesn't have to be on the wire. It doesn't have to be on the wire at all. It could just be somewhere in space like here. But the point is that if this were connected by some gossamer, etc., to the wire, and you balanced the whole concoction on this point, somehow the whole thing would balance. It's sort of hard to imagine, but it would balance from any angle if there was, regardless of where the gravity was. It's really the central place of this point. It's easier to understand in 2 dimensions. If the wire is in 2 dimensions and you have this little net going there, it's the point where the thing would actually balance. So for example, if the wire were a constant density loop, then the center ought to be the center of mass, even though it's not in the wire. So if you did stretch these spider webs between, that's where it would balance, not over here, then the wire would tip down. It's exactly the same set of formulas. And of course you have a set of inertia formulas as well. The inertia of this wire as a rotation about the x-axis is the second moment. And etc. for IY and IZ. So I don't want to reinvent the whole thing here. We already did this for double integrals and triple integrals, and it's not much difference for a line integral. Again, it looks like you have to do 4 line integrals, and it's true, but luckily you can use the same parameterization for all 4 integrals, for the m and for these 3 first moments. You can use the same parameterization. So once you find the parameterization and you find the speed, the only difference between the integrals is this extra x, y, or z that comes up. So it's not 4 times as much work. All right, and again, I haven't really seen very many questions in previous finals or quizzes about centers of mass and inertia. That doesn't mean it's not fair game, but it's sort of, it seems to be lower on the priority list, mostly because it does involve doing 4 integrals, even if they are related. And so it seems different types of questions than ones that rely on a lot of computations. But that's just a philosophical point. All right. Are there any questions about the basics of line integrals? Yes?
It's not exactly about a line integral, but it's in the same section.
Okay.
what exactly is integration over a plane curve, and how does that relate to line integral?
Okay, so the question is, what is an integration over a plane curve? That's a two-dimensional line integral like this. Okay, not a three-dimensional. Okay, so the curve C lies in a plane. So you have f of xy, and the ds is the same as it was before, but you don't have a dz dt. It's just the square root of dx dt squared plus dy dt squared.
Okay.
Okay, I think that's what it means. Okay, so it works in two dimensions as well.
Did you cover doing this in vector fields yet, or?
I haven't started vector fields. That's okay. Are there any other questions about anything I've said so far?
Where would you usually use the I of x?
I don't know. If you're doing physics and you want to know a moment of inertia, right? So here's moments of inertia are useful for knowing how much work you need to do to get a certain object up to certain rotational speed, right? So you want to rotate something around, and how much energy do you have to use to do it, right? Now, it's moment of inertia is a sort of mass with respect to that. So I want to know how heavy this book is so I can pick it up, right? So I know how much force to do. Okay, I want to know how heavy the inertia is, or how much the inertia is, because I need to start turning this thing around there. Right? The more it is, the harder it is to get it up to a certain rotational speed. So if the thing happens to be a wire attached to a pole, which I want to start moving around that pole, I might want to know what its moment of inertia is before I start doing it. Okay, so it definitely has applications. I mean, certain things are in cables, like on a bridge, you know, cable on a bridge. That is modeled by a line integral. Okay, so there's a lot of practical applications to this. Anyway, speaking of vector fields. All right. Move on to 16.2. Okay, here's the deal. If f of xyz was a scalar function, at every point x, y, z, it gives you a number. But what if it gave you a vector? As in, instead of coming back with a number when you say supply x, y, z, it comes with a vector. So I'll do the three, actually, I don't know, I'll do a two-dimensional example first. So I'll use capital F as the textbook does. Of course, you can use any letter you like, as long as it's bold or underlined or has an arrow on the top or something like that. So this is now a function of two variables that gives you back two numbers instead. So I'll follow the textbook convention, write it like this. But in principle, it could have been written as in sort of coordinate vector notation like this. M of xy comma n of xy. So for every xy pair you supply, you don't just get one number, you get two numbers. You get some multiple of I plus some multiple of j. So this is a function from two variables to two variables. But the nicest way to think about it is this. Suppose the domain is somewhere around here, you know, it could be the whole plane, whatever. Here's x, here's y, otherwise known as ij. But to emphasize that it's a vector, suppose I plug in this value of x comma y, I don't know, 1 comma 3. I don't just get back a number, I get back a vector. So what I want to do is actually draw the vector in here. So suppose this is f of 1 comma 3. Now let's try a different point, 2 comma 2. Plug that in and you get some multiple of I plus some multiple of j. And again, I'm going to consider it as a vector whose base I'm going to draw on top of the point. So that might be like this. So for every point, no matter where it is, every point has a little vector attached to it. Different points have different vectors. Now, in principle, these vectors could be all higgledy-piggledy. But what I want is, I want it to be that when 2 points are very close together, their vectors are quite close together, in the sense that the lengths and directions of vectors are very similar. And the closer the points, the closer these points are. So that would be continuous. I'm even going to need it to be smooth. Practically speaking, smooth means differentiable, or maybe sometimes twice differentiable. F is going to be smooth if M and N are smooth. So as long as you can differentiate these both, then this is going to be okay. But if you have things like absolute values there with sharp corners, then that's going to be a problem, and it won't be a differentiable vector field, at least. So when we say vector field, we mean that it's smooth enough. I should really specify that, but often I'll forget to say it, so I'm saying to you that I'm going to assume these things are smooth. Now, these things are actually very useful, and you've seen them before. You've seen them on the Weather Channel. Okay, when they show ocean currents and wind currents, they'll show you a little map of contour lines, and sometimes they even have these vector lines, current maps and all that sort of stuff. Those are vector fields. At every point, there is a vector attached that shows you how fast something is going at that speed, at that place, rather. So it could be, for example, how fast the wind is going. So the interpretation is that at this point, this vector, the direction indicates which way the fluid, the air, the water, whatever it is flowing, and how long it is indicates how fast it's going. If there's a zero vector, meaning both of them are zero, then something there is not moving anywhere. It's just staying still. Well, that may not be true. Technically, I throw the chalk up in the air, it comes back down. At the top, its velocity is zero, so it's not going anywhere. The reason it's not going anywhere is because it sort of has finished going up, it's about to go down. It doesn't mean it's standing still. But apart from that, that's what a 0 point is. It's locally stopped. Then could start again. Okay, so the concept of vector field. Is this clear enough from what I've said? Or does anyone have any other questions about the basic idea of it? No questions? All right. Now, 3 dimensions is exactly the same, except there's a z, and there's another function p. So, might look something like this. M of x, y, z, I, plus n of x, y, z. It's almost silly to write this out, but just for completeness, plus p of x, y, z, k. All right? Yeah, a lot of letters. In reality, you almost never write m, n, and p. They're sort of more just for the formulas to get a grip on it. But in reality, yeah, you just kind of write down what the functions are and insert them in there. All right, so let's discuss integration of a line integral type, but in a vector field. Oh, actually, before I do that, let me say the most important example of a vector field. You start off with a scalar function, f of x, y, z. Then grad f is actually a vector field. This is a vector field. By definition, this is df dx, lots of I, plus df dy, lots of j, plus df dz, lots of k. So this is a vector field. This is your m, this is your n, and this is your p. So it's a vector field. And it's called the gradient vector field. Even though this is a scalar function. So they like to write this in bold in the textbook. I mean, maybe I should put an underline, but it's always a vector. So grad f is a vector. It's a gradient vector field. All right. Now, what I'd like to do is I'd like to imagine this field in space or in a plane. It doesn't matter. It works in 2 or 3 dimensions. Okay, so there's a field of vectors. And now think of it as a force field. Okay, visions of Superman or comics, whatever. When I say a force field, I'm kind of thinking, well, this is the amount of force that is exerted on a particle at different places of space. So the easiest way to imagine a force field is on the Earth. There is a force field on the Earth. Well, the vector, let's call the vector in the direction of the force. Right? There's certainly this force field here. I mean, if you're near Earth, bang, force. So actually, it gets weaker as you're further away from it. I'm not going to draw in every arrow because there's infinitely many, but the closer you are, the stronger the forces. Okay? So the question is, how much work is done on a particle going through a force field? It depends on the path. So suppose I have a satellite falling to Earth like this, or going against Earth, a rocket, if you want to go the other way. How much work do you need to get it through this force field of gravity? So the answer is, you want to form a line integral. Work integral. So the work done through the force field F, force vector field F, is defined to be an integral that looks like this. F dot t ds over c. And we don't quite know what this means. Well, t is a unit tangent vector to c. So you have this curve here, and you have these force vectors, but I also want to consider the tangent vector along the curve. And what I want to do is at every point on the curve, as the function that I'm integrating over. This replaces the little f of the previous section. Okay? Remember, the dot product between two things is a scalar. So this is just a regular scalar integral. And so it's a form of line integral, but it starts with a vector field, and then you have to dot it with the unit tangent vector. And the reason this works is because, actually, if you have a force going this way, and you try to move it this way, it doesn't take any work at all. So, in particular, if I want to lift a heavy object, then it doesn't really take any work to move it along here. Well, it kind of feels like it does, but actually think about it. If you're on a frictionless surface and you just want to kick it, it'll just slide. There's no work done. If you want to pick it up and it's heavy, then you have to work against the force field. So basically it's only the direction parallel to the force that counts. And the dot product gives you the cosine of the angle. Cosine 0 is all of it. Cosine pi over 2 is 2 of it, none of it. So it turns out that if you chop this curve into many little different pieces and look at the actual work impacted there, the dot product of the tangent vector, which is along here, with the force vector is exactly what you need. Now, how do you compute this? Well, the question is, what is the tangent vector? The velocity vector, if you've parameterized the curve, the tangent vector is just the velocity vector. But that's not a unit tangent vector. The way to make it into a unit tangent vector is to divide by the speed. And here you really hope that's not 0. If it is 0, you might be okay. You'll probably get an improper integral. But it's actually not as bad as it looks, because ds in this parameterization we've already seen is v of t dt. So there's a bit of cancellation. This work integral becomes the integral from t0 to t1. The force is well, actually, I probably should do a tiny little bit more work. Well, okay, no, this will do. Now, this is at a point t. So this is substituted here. Really x of t, y of t, z of t, like we did. And then you dot this with v over v. That's the tangent vector. And then you multiply by the speed. ds becomes the speed dt, and these cancel. So the actual formula that you need is just this. No speed necessary. It's just f at the parameterized point t dot the speed, the velocity vector dt. And this is work. Equals that. So let's do an example. Where is it? It's from review sheet number 9, and it's problem 3. Oh, before I do it, I should say that because of this last computation that I've done, the v of t dt is often written as dr, right? We saw that if r is the position, then v is dr dt. If r is the position, v is dr dt. So this integral f of t dot v of t dt is the same thing as f of t dot dr of t. And so often these line integrals, these work integrals, another way of writing it is just f dot dr instead of f dot dt ds. So that's just a different notation for it. Yes, question?
If we had to compute something that way, just using fdr, dot dr.
Yeah, in fact, this question that I'm going to give you is exactly that. But no matter what you do for the computation, you always have to convert it to a parameterization. Okay, so these are just different ways of writing the concept, but the parameterization is going to give you the answer. I say always. If I have time, I'll do Green's theorem, which allows you to avoid some of these computations by doing double integrals instead. But anyway, hopefully we'll have some time to do that. All right, so here's the question. Let C be the closed curve in the xy plane consisting of the part of the parabola y equals x squared from minus 1, 1 to 1, 1, and the line segment joining these points. Well, it says let C be the parabola that joins the part of the y equals x squared that joins this to this, and the line segment that completes the curve. So rather than doing anything, I'll just draw it for you. It looks like this. You start at minus 1, 1. You go along the parabola y equals x squared up to 1, 1, and then you go back along the line segment. So the direction is important here. It's actually a closed loop there. It says we equip C with counterclockwise orientation. So this is our curve C, as interpreted from the question. And then the question is to compute f dot dr, where f is the vector field in 2 dimensions given by 2xyi plus x cubed minus y cubed j. Okay, so it's a 2-dimensional integral of this work type. All right, how do we do it? Well, first of all, we're going to have to split into 2 pieces because the curve has sharp corners here and here. So we're going to call this one C1, C1 parabola piece, and C2 line piece. It's a piece of the line. Okay? So let's do C1 first. How do we parameterize the parabola? We need a parameter. Well, I mean, you know, if it was a circle, I'd start looking into cosines and sines, but the easiest parameterization is just to let x equals t and y equals t squared. That'll do. And of course, t then goes from minus 1 to 1 because x does. that's the correct direction as well. That will give you the parabola going around from there to there. Okay, so there's a parameterization. So in other words, r of t is equal to t comma t squared. So we need the velocity vector dr, otherwise known as v of t dt. That's another way you can write this. Dr is just 1 comma 2t dt. I just differentiated the t and the t squared. Okay? I put the dt in there because there's a d over this side. All right, now we have to work out what f is. In our case, x is t and y is t squared. So I plug these in. I get 2t t squared I plus t cubed minus t to the 6th j. Or as a vector, this looks like 2t, I mean in coordinate vector notation, 2t cubed t cubed minus t to the 6th. So now, I'm ready to do the integral, at least for that piece. And then we'll have to come back to C2, the second piece of the curve. So the integral over C1 of f dot dr is equal to the integral from t equals minus 1 to 1. F was 2t cubed minus t to the 6th dot dr. dr is 1 comma 2t dt. So this is the f and this is dot dr. And you see why the parameterization is critical. Not the choice of it, but just choosing something so you can even get started. Okay, so this is just a dot product of two vectors. So it's this times the first quantity, 2t cubed times 1, plus t cubed minus t to the 6th times 2t dt. Nothing to be scared of here. This is a regular integral. 2t cubed plus 2t to the 4th minus 2t to the 7th. 2 looks like a common factor. I'll pull it out. T to the 4th over 4 plus t to the 5 over 5 minus t to the 8 over 8, evaluated between minus 1 and 1. And actually, because this is even, the 1 and the minus 1 will cancel out. You get a quarter minus a quarter. The same with this, and you'll actually just get the t to the 5th part. So if you work this out, it turns out to be 4/5. And that's the value over there. All right, I'm going to do the C2 curve now, which is actually a line segment. But before I do that, I just want to make sure that you're all cool with this part here. See how I did it? Choose the parameterization. To find f, you just plug in x and y. To find dr, you just differentiate the r vector that you've chosen. It's not too bad. Not too bad at all. Just have to practice these things. Any questions about it? Let's do the C2. So we need to parameterize this line segment here going from 1, 0 backwards to minus 1, 0. Well, the y-coordinate is always 1. So the x-coordinate we could take to be t again, but this time t goes from 1 down to minus 1. That will work. There's different parameterizations, but to me it's just simpler to take x equals t and y equals 1, but just remember t is going to go from 1 backwards to minus 1, because we're going counterclockwise in the original curve. So the r vector is very simple. It's t comma 1. dr is 1 comma 0 dt. I just differentiated t to get 1 and 1 to get 0. Also f I got to take this 2xyi plus t cubed, x cubed minus y cubed j, and I've got to substitute x equals t and y equals 1. So we'll get 2ti plus t cubed minus 1j. As a vector in the coordinate notation, you get 2t comma t cubed minus 1. So the integral of C2 dr is the integral from t from 1 to minus 1. Just make a mental note that it's sort of backwards. It is backwards. F is this vector 2t t cubed minus 1 dot the dr vector 1, 0 dt. And this is the integral from 1 to minus 1, 2t dot times 1, and then the 0 kills off the other coordinate. So it's just 2t dt. Well, we better reverse this into minus the integral from negative 1 to 1, 2t dt, which is very straightforward. In fact, it's the integral t squared minus t squared from negative 1 to 1, which works out to be 0. So this piece is 0, and the integral we're looking for, the closed is 4/5 plus 0. We add up the two pieces. You get 4/5.
So the second part being 0 is saying that along that second line segment, the function value doesn't change at all.
No. If the function value didn't change, say the function value was 3, right? Then actually the value of the integral that you would get would be 3 times the length of the thing. Instead, it's a fact. It's more of a factor of being that the function is odd along here, as it turns out. F is 2xy I plus x cubed minus y cubed j. And both of these, when y is 1. So the point is that the y value doesn't change, but you're actually only going along the x value here. So the x coordinate is the only thing that matters in the line integral. So the y value of the force is changing. I will give you that. Right? As t changes, this value changes, and it's not an odd function. Okay? But when you're moving a particle from here along here, the force in this direction doesn't matter. It's irrelevant. It's only the force in this direction. And that's an odd function. So for every bit of work that you do here against a force pushing you, say, that way, you get this energy back, or it's like a negative work on exactly the same point on the other side. And you it's a zero-sum game. You've had to expend work in one direction, and you expended energy in one direction, and you gained the same amount of energy in the other direction against this force. And that's because the 2t part is an odd function of t. It's positive when you're on the right, negative when you're on the left. Actually, that's not quite true. T is positive here. Yes, okay, it is positive when you're on the right. It is true. So the force field looks like this in the... That's the x component of the force field. The y components, at t equals 1, it's negative, it's 0 rather, and then it's becoming more and more negative. But that doesn't matter, because you're not moving it against that direction. For the parabola, it does matter, because you're moving it in both the x and y directions. So you're subject to some of the force of each. Does that make sense?
Yes.
Okay. So it happens to be 0, but that's only because what you lost, you gain later, or vice versa. Another question.
Could you explain how the unit tangent vector idea factors into this?
Yeah, well, essentially, the line integral has a ds part. And the ds, which is the arc length, is the speed of your parameterization times dt. So if you have a different parameterization, you have a different v for that little piece. Okay? But that's okay, because you have a different function as well, and somehow the chain rule ensures that you get the same value. So the ds already has the speed. But the unit tangent vector is the velocity vector divided by the speed. And so the speeds cancel out.
So you're not really seeing anything tangent, like the force field isn't tangent to the curve or anything.
No, it doesn't have to be. It doesn't have to be. But taking this dot product means that you only see the part of the force field which is tangential to the curve. So you've sort of given a curve like this, there's a tangent vector. If at this point the force field is like this, then what I'm really doing is projecting the force onto here and saying this is the only part that counts, because I'm moving it along there. This part of the force I can't see, because I'm moving it perpendicular to it. So the Exactly. And the only point about the speed is it's sort of a correction. You don't actually need the speed, as it turns out, because if you do go twice as fast, then the F will move twice as fast, and everything will work out fine as a result of the chain rule. It's sort of like doing a substitution, u equals 2t. That will change the integrand, right? But it also changes the limits of integration, and it gives you a 2 dt. So all these factors in the chain rule will just cancel each other out. It's kind of nice. It's really nice how you can use any parameterization. And that's, again, it's the chain rule, but I haven't proved it. But it works out. So in this example, you know, the tangent vector is 1, 0, or actually the negative of it, because we're going backwards. And you can clearly see that the y value of the force doesn't even matter, because when you take the dot product, the 0 kills it. So it's easy in this case because the y component is 0. It's a little harder in this case because the y component's 2t and this is 1. But still, the dot product essentially then gives you a decomposition like this. It's at an angle. So you just find the part of the force that's in the same direction as the tangent. And then, of course, as the curve moves around, the tangents move around, and so, but the integral takes care of that. It's continuous calculus. Any other questions about that? But you see the actual computation's not so bad. You have to come up with the parameterization, r, but the dr is exactly the derivative. F is just plugged in, and you just take the dot product and do a regular integral. So they're not terrible to compute by any means. Okay, so that's the idea of a work integral. Next, I have to give you the idea of what's called a flow integral. Well, the good news is that it's the same thing as a work integral. Okay? Here I was considering F as a force field, so it's like gravity. But now think of it back on the weather map. It shows you how fast something is going. So the wind is going at different speeds. At this instant of time, the wind is going at a different speed and in fact, different directions, so a different velocity at all points around the Earth. We can actually draw what the field looks like. We just have to stand at every point on Earth and measure the wind speed and direction and map that. Of course, it's going to change over time, but right now, there it is, there's a field. And so imagine the wind never changes, that's the field. Okay, so now I'm going to take a particle, I'm going to let it just meander along some sort of curve there, and I'm going to define the flow as just the same integral, f dot dr. Okay, that's called the flow of the thing. So, okay, that's just physics. I'm just giving you a different name for the same thing. But to celebrate, let's just do one more problem. Okay, so this is from the textbook. F is the vector field xyi plus yj minus yzk. So this is now a three-dimensional vector field as opposed to the two-dimensional. And you're asked to find the flow from 0, 0, 0 to 1, 1, 1 along the line segment. Yeah, find the flow. You just have to realize that this is a velocity field. Okay, whatever. It's just a work integral in disguise. Oh no, not along the line segment. That's not what the textbook said at all. Scratch that. It was along the curve of intersection of the cylinder y equals x squared and the plane z equals x. And there's a picture of it in the textbook. But in any case, I will refer you to the picture, but you actually don't even need it. You see, this tells you exactly what to do. This tells you exactly what to do. If you take a parameterization of this curve where x equals t, then hey, it's got to be y equals t squared, and it's got to be z equals t. That's the curve lying along these things. I mean, we know exactly what y is if you know what x is. You know what z is as well. So there's your r vector. R is t squared, t. So dr is 1, 2t, 1 dt. Also, f is equal to x is t, y is t squared, y is t squared, y is t squared, and z is t. So that works out as t cubed t squared j minus t cubed k. And so the integral, the flow integral, otherwise known as the work integral, again, if f is forces, then this is work. If f is velocities, then this is flow. Along this curve C mentioned here, it's clearly going to go from t equals 0 to 1. When t is 0, you get 0, 0, 0, and when t is 1, you get 1, 1, 1, which is the final point. So t goes from 0 to 0. F is t cubed, t squared, minus t cubed, and that has to be dotted into the dr, which is 1, 2t, 1 dt. So this is t cubed times 1 plus t squared times 2t plus minus t cubed times 1 dt. T cubed, 3t cubed, back to 2t cubed. So that's t to the 4th over 2. 1/2. Okay, this is another computation example. Any questions about it? Not particularly interesting, I'll give you that.
You didn't even look for you didn't even try to describe the curve for the intersection.
Yeah, well, I really should have, but there's a nice picture in the textbook. It's in section 16.2. It's one of the problems. I forget which one. I'll tell you which one it is. Well, you have the textbook close by. It's 16.2, problem 43. There's a nice picture. But, you know, normally I encourage drawing a picture, but I'm kind of short on time, and there's a nice one in the textbook, so I thought we'd give it a try without it. It worked pretty well. All right. Now, if you have a closed loop, sometimes you write the integral like this, with an arrow somewhere on it. All that means is that C is a closed loop. The direction is counterclockwise, but I guess the arrow could be the other way, which would mean clockwise, and that you only go around once. If you go around twice, you'll get twice the integral. If you go around backwards, you'll get as in clockwise, you'll get minus. That's a notation. The arrow can be over here, anywhere. It's just the idea. Okay, so no need to be scared of it. It's just a closed loop. Now, I've told you about work or flow, but now I have to tell you about something called flux. It's getting much more like Back to the Future every second here. Flux capacitor. Okay, here is the idea. It's another line integral that I'm going to do. I want to define this integral. F is a vector field, but instead of dotting with the unit tangent vector, I want to dot with the unit normal. Now, in principle, this could be done over any C. However, for practical applications, the C should be a closed loop. And there's a good reason for this. What is a normal? Well, the normal is perpendicular to the tangent. So if here's a curve, there's the tangent, here's a normal. Which normal is it? Could be that normal. That's another unit normal. There's always two unit normals for a plane curve. However, if this happened to be a three-dimensional curve, then you'd have a whole host of unit normals. So that starts to become tricky. And there's a section on the book that we kind of skipped to discuss what they are. For our purposes right now, we're just going to take a two-dimensional curve. So I'm going to consider this to be all 2 dimensions. And I want to take a closed curve for one reason, and one reason alone, as far as I'm concerned. Because now there's an idea of what's an inside and an outside. Right? Okay, sure, the curve could cross itself, but I'm going to take a curve which doesn't cross itself for simplicity. It's just a simple, closed, smooth curve, or piecewise smooth. You could still have a corner here, a few corners. But N is going to be the outward normal, and it's unit normal. So at every point, there's a tangent, and there's a clear in versus out distinction. So N is the unit, so it has length 1, outward, so it points out of the curve, normal. If the curve is not a loop, as in not a closed curve, then there's no difference between out and in. I mean, what's out, what's in? But if it's closed, you can easily tell. All right.
Can you have flux over a partially closed loop?
It doesn't really make physical sense. It doesn't make physical sense unless the loop is closed. All right, and these fluxes definitely have physical, I mean, all this stuff in multivariable calculus is essentially inspired by physics. Electric charges, the whole electromagnetism requires all of this stuff that we're doing in order to make sense of it. So it's only right that in this math course we actually use words like flux instead of some mathematical term which wouldn't have anything to do with flows. All right, now here's the question. Given a curve and a parameterization, how are you going to find the unit normal? Well, there's a very nice, clever way of finding it. Suppose we're on this curve and we have a tangent vector t. We know how to find the tangent vector, right? T is the velocity vector over its absolute value. That's the unit tangent vector. Okay, it should have the same length as n. So suppose we took the vector k. So this is in 2 dimensions. There's I and j. Actually, j is normally up. I is right. K goes out of the board. K is just the z direction. So it's out of the board. So imagine we took t cross k. Well, that's a vector. It's a cross product, so that vector is perpendicular to both t and k. Here's t. Here's k out of the board. Guess what? It's going to be n. Or perhaps minus n. But it turns out that it should be the outward normal if you're going counterclockwise. And to see why, you have to use the right-hand rule for that. T, K, N. And that's the same as you walk away, as you go all the way around. So this is exactly what we want. Now t, of course, was v over v. So n is t cross k, which is v over absolute value of v, or the length of v, cross the k vector. And if you remember in our parameterization, so this is 1 over v. I'll just pull that out. And I'll set up the determinant for the cross product. I, j, k. The velocity vector had components dx, dt, dy, dt, but the k coordinate is 0 because I'm taking a parameterization of this curve x of t comma y of t in the plane. There's no z coordinate. This is just a planar curve. So the k coordinate is 0. But I need to, so that's v, that's the v vector here. I need to cross that with k, which is just 0, 0, 1. That's the one pointing out. So what do I get? I get 1 over v, and then this is dy dt, lots of I, minus dx dt, lots of j. And if you work it, the k coordinate is 0, because this times this is 0, this times this is 0. So that's what the unit normal looks like. That's what the unit normal looks like. And so in our integral, f dot n ds, this is equal to f of t, going from t0 to t1 again, dot, well, what's n? N is this weird vector, 1 over v of t, times dy dt I minus dx dt j. But then the ds itself is v of t dt. And again, these things cancel. And so you get something a lot more palpable. And I will write it out now. That was all theory, by the way.
Why is v times k equals 1?
You mean v cross k?
V cross k, yeah, sorry.
Who said v cross k is 1? Where do I say this?
Ah, sorry.
Okay, you are forgiven. All right. So, in particular, here's the deal. If f, the vector field of xy, looks like m of xy, comma, or times I, plus n of xy, j, then f dot n ds around this closed loop, parameterized by t, is going to look like, we need the y coordinate of f, which is dn dt, and then we need the, well, how do I want to write this? How do I want to write this? Let's write it like this. Minus the x coordinate no, I've left out the f. I don't think there is a simple way of writing it. What I've written down here, I don't like at all. I've kind of mixed up the form stuff. Okay, let's just write it like this. Let's just rewrite what we had. T, 0 to t, I need f of x of t, comma y of t, dot dn dx, comma dm dy. And this is all in terms of t. Now, things have gotten sufficiently complicated that I ought to introduce what's called differential forms. So instead, let's not have so many dt's around and look at forms. I've already shown you the form like this, f dot dr. That's a sort of differential form. Now what does it mean? Well, suppose f is exactly as above, so f is this, is written as x of t, y of t. So dr, this is in parallel with what we've been doing before. Forget the normals for the moment. Dr is dx dt, dy dt, dt. And so this integral is the dot product of, from t0 to t1, of m of xy, comma, n of xy, dot dr, which is this, dx dy, dx dt, dy dt, dt. Now, suppose that we kind of cancel out the dt's. And don't worry about this for the moment. Let's just write this as, go back to C. This is going to be m dx plus n dy. Right? So this is m dx plus n dy. So this is called a differential form method of writing down exactly the same thing as what we've written down before. And almost just to really nail down the point, and then I'm sort of taking an aside from what we've just done. Let's just go back to this question here, where we had the contour r of t was equal to t squared t, and we had f of t, well, we had f of x, y, z was this mess here, xyi minus plus yj minus yzk. All right, so the deal here is that one way of writing this, f dot dr along this contour, you could write this as xy times dx plus y dy minus yz dz. Okay, that's a generalization of this, where I have m dx plus n dy plus p dz. Well, here's the dz part. So what I'm trying to say, these are just different notational devices for the same thing. This is not a new concept. This is just saying, okay, I could have asked you, find that integral, where c was specified as before. Instead of writing it like this, I could have just said, find this. And I want to show you how you get exactly the same thing. I'll show you how you get exactly the same thing. Under this parameterization, if x, y, z is equal to t squared t, then dx, dy, well, let's just do dx. dx is just dt. dy is 2t dt. And dz is just dt. I've just differentiated these things. And so if I plug this in here, again, t goes from 0 to 1 in this parameterization. X is t, y is t squared, and dx is dt. Y is t squared, dy is 2t dt. Minus, I can't quite fit it in, but that's okay. Y is t squared, z is t, and dz is just dt. And of course you get exactly the same thing we had before. It's just that each piece has a dt, but you collect them together, you get t cubed plus 2, and it's again 2t cubed dt, which is a half. So I just want to emphasize that that's exactly the same as what we did over here. There's no difference. It's just I kind of assembled them differently. There's the xy dx, which is here, with the dt included. The same with the y dy and the z dz, or the minus yz dz. Okay? So is that clear how this is just an alternative way of writing it? I mean, all I've done is explicitly write out the dot product, actually, is what it comes down to. Right? Does that make sense? It's not anything new, as I say. It's just a different way of writing out the same problem. Okay, so if you have f dot dr, that integral could be written as that differential form integral. Now let's go back to this flux integral here. Well, before I do, for planar curves, I'll just write this out once more to really nail this down. So if f of xy is m of xy I plus n of xy j, then the regular sort of work integral, whether or not it's actually closed, f dot dr, is equal to m dx plus n dy, with the idea that you're going to replace this dx by something dt and this dy by something dt. The normal integral that we looked at just a few minutes before.
Why is that?
Why is this?
Why is the second line?
Here?
Yeah.
Well, it's just here. F is m comma n, and dr is essentially dx comma dy. And so when you dot them, you get m dx plus n dy. Okay, but if you look at back over what I have here, you have a dn dx dm dy. And guess what? I left out a damn minus sign. Oh, hell. The minus was over here. No one said anything. I forgive you. So here, according to this formula, you have to dot n with dy and m with dx. You know, there's a real problem here. This is not right either. Ugh, this is horrible. This is supposed to be r in both cases. It's the path. It's the path. Man, I really butchered that. Please go back and correct that. Yeah, the m and the n only come into effect with the f. But anyway, here it is in a nice clean fashion. And this is the fashion in which it's easiest to compute these things. So this is the way to learn them, I feel. Okay? Here it is. Now, better do an example. Here's problem 4 from set 9. So, you're given the velocity field F is x over x squared plus y squared all squared I plus y over x squared plus y squared all squared j. And you're concerned about C being the circle x squared plus y squared equals 4. That's a closed curve. Question.
The book says that is n times dy.
Minus n times dx.
It's been a rough night. The book is right. Ah, I don't know my m's from my n's. Go back over here. This is m. This is all screwed up. I could look at it until I'm blue in the face, and it still wouldn't look like what I wrote down over there. So let's just go over here. And forgive my incoherence. The derivation is not quite right. I almost had it, but I kind of stumbled at the end. So if there's any justice in the world, you end up with this. Now, the book, does the book say n dx minus m dy?
No, n dy minus.
So I have it right, finally. Yes? I do have it right. I should have it right. It does make sense. But I just don't want to have it out by a sign as well as all wrong. I don't seem to have written it down in my notes. I was away in Montreal all weekend and I did not have enough time to prepare this. Oy, oy, oy. M dy minus n dx. Okay, very good. Now, let's do the problem. This time I might even get the right answer. Okay, here's the curve. What I'm asked to compute is the flux integral f dot n ds, bless you, around this curve, closed curve. Now what I'd like to do is set up a parameterization. So for the circle, the easiest thing to do is let x is 2 cosine t and y is 2 sine t. Standard polar coordinates, but the radius is 2. So dx is minus 2 sine t dt, and dy is 2 cosine t dt. All right, well, according to the corrected formula, the best way to write this is m dy minus n dx, as opposed to m dx plus n dy. So the m's and n's are scrambled. If you go back over what I did and just correct a few stupid letters that I wrote down wrong, you'll find it's there. It works. I just had an error in translation, as it were. Okay, so in parameters, t here goes from 0 to 2 pi. That will get us once around the circle. And I'm going from 0 to 2 pi. M, well, this is m. And this is n. I hereby dub these coefficients of I and j, m and n, respectively. So m is, well, maybe I should write this out. Give me one more step before I switch to parameters. M is x over x squared plus y squared all squared dx plus y minus n y over x squared plus y squared all squared dx. Ta-da! Finally, I think I got a formula right. There's the m, there's the dy, there's the n, and there's the dx. All right, so what does this look like in parameters? First of all, I plug in x, which is 2 cosine t. The bottom, x squared plus y squared, is 4, because it's cosine squared plus sine squared. And then we have a square, which gives us a 16. But we need the dy. dy is 2 cosine t dt. Minus, repeat, y itself is 2 sine t. The denominator is still 16. dx is minus 2 sine t dt. So if you work this out, you get 4 cosine squared plus 4 sine squared, which is 4. So 4 over 16 times the integral of 0 to 2 pi dt. So there's a dt there and a dt there. So it's 2 pi times a quarter. I didn't even get the right answer on my page, but that's what it is. All right, so we know how to do a normal integral. We don't know why, because I screwed up the derivation. But if you believe what's in the box, then it's not so hard to work these things out. Question?
So this makes sense.
Good.
In 2 dimensions, but for 3?
Yeah, for 3, we're not going to do it in 3 dimensions because there's some question as to what the normal is. And in order to do this, you had to start talking about skewness of curves, and we skipped that section. So you can do this in 3 dimensions, but we can't do it because we missed something earlier. All right, I still have a few minutes. I'd like to touch upon 16.3. I'm not going to get Green's theorem done, and I apologize. Some of that time was wasted by this not correct formulas, but I think we've sorted that out. So let me talk briefly about conservative vector fields. At least start the discussion, and then next week I'll continue it. So it goes something like this. If I have an integral, forget the normal integral, just do an f dot dr over some curve in space. It doesn't have to be closed, as long as it's smooth or piecewise smooth. Okay, so here's the deal. If you just know the starting point and the ending point of the curve, say this joins A to B, then you don't know enough to do this integral. You do not know enough to do this integral. because it depends on where the curve is and how it goes from A to B. Different curves will give you different values of the integral. Okay, but sometimes it doesn't. Sometimes it doesn't matter. So put into if f happens to be the gradient vector field of some function little f. And remember, when I first showed you about vector fields, I said a very important example is the gradient vector field of a scalar function. So if that's true, then the integral looks like this. Now, this is a nice point. Suppose that the region of the domain of little f is some region which doesn't have any holes in it. So that's bad. We need it to be what's called simply connected, no holes. And also, we don't want it to be in two pieces either. It needs to be connected. That's no good. So it has to be basically be a blob with no holes in it. Or in space, it could be a chunk of space without any holes. And just one chunk, not two. So that's called simply connected and connected. So let's assume that's the case. If this is true, then this is equal to f of b minus f of a for any c joining any curve, piecewise smooth curve, so any nice curve joining A to B. Beautiful. It's beautiful. It's just stunning. It's a fundamental theorem of calculus, actually. The integral of the derivative, because the gradient's a derivative, is the function at the beginning minus the function at the end minus the function at the beginning. I sort of have time for one example. Okay, I'm missing one particular thing. If this is true, then f is exact. You say f is exact, or conservative is the word I'm going to use for the moment. It has nothing to do with politics. It has to do with conservation of energy and physical quantities like that. So if this is true, that it's conservative, next time, I just don't have time now, I'll tell you how to tell if a vector field is conservative. But suppose I give you this simple question here. Let f be equal to x squared plus y I plus y squared plus x j plus e to the z k. So the question is, I'll give it to you that this is conservative. So the question is, find the potential function. F is called the potential function of the vector field. It's sort of like an antiderivative of it. So basically, I'm going to tell you that there is such an f, and most of the time there isn't. It's a very special case. So the question is to find it and use this to evaluate f dot dr, where C is any curve joining 301 to 211. And they call this A, and they call that B. So I'd like to just show you how to do this in the last minute, and then we'll stop. Okay, so what I want is, I want f to be equal to df dx, df dy, df dz. These should all be partial derivatives. So I want that to be the case. And I don't know if this is going to work. So there's a test, as I said. I'm just going to go ahead and pretend that it's going to work. So this has got to be equal to x squared plus y, y plus y squared plus x, comma e to the z, because that's what capital F is. So if this is true, I've got to solve three equations. df dx equals x squared plus y. And I'm going to need df dy is y squared plus x. And I'm going to need df dz is e to the z. That's what I need. Okay? So if this is true, I can integrate with respect to x. So integrate this with respect to x. And you will see that from this equation, f has to be x cubed over 3 plus xy, I'm integrating with respect to x, plus a constant, which I call c1. Now that's a constant in x, but it could be any function of the other two variables. It just has to be when you differentiate with respect to x, you get 0. So it could be any function of the others. From this, we get the same thing, but we integrate with respect to y. And you get f is y cubed over 3 plus xy plus some other function of x and z this time. And finally, when you integrate this with respect to z, you see that f has to equal e to the z plus any function of x and y. And if we can somehow make these things consistent with each other, then we're done. This is not going to take much longer. Sorry to go a couple of minutes over. I claim that if we just bung all the pieces together, we'll get what we want. We have an x cubed over 3 and an xy from the first one. In the second one, we have already got the xy, but we need a y cubed over 3, which doesn't depend on the x. And then for the z part, we have an e to the z. And then all that's left is just some constant. But now that's a real, actual constant. If you look at this, you will see it's compatible with all three of these. F is x cubed over 3 plus xy plus some function of just y and z. So this would be c1 of yz. But it also works for the second one. It's y cubed over 3 plus xy plus some other function only depending on xz. And finally, f is also equal to e to the z plus some function of x and y. And the only thing remaining is just some constant. You can never get rid of that constant because when you differentiate with respect to any variable, that goes away. So that is the potential function. And in fact, you don't need the c. A potential function, we can get rid of the c. Plus c, not necessary. At least to finish the problem, it's not necessary. The integral we're looking for, f dot dr, according to what I just said, is just little f of b minus little f of a. And b is 211. A is 301. So I just plug 211 into here. 2 cubed is 8. 2 times 1. 1 cubed. E to the z is just e. Minus, plug 301 in. You get 3 cubed over 3. xy is 0. Y cubed is 0. And z is 1. So the e's cancel out. You get 9/3 of 3 plus 2 is 5. And minus 9. So it's negative 4 is the answer, as it turns out. And it doesn't matter which curve you use. I guarantee you pick any curve joining these 2 points, plug the thing in, try to do the integral like we've done previously, and you will get minus 4. And it doesn't matter which curve you use. A quick question.
Do you know that function's conservative as long as you can solve something like that?
If you can do that, it's conservative. But there's an easier way to check first, which I will do next time, but so that you don't have to go to the trouble of trying to match them up. It guarantees that that will work in particular. All right, sorry to go over.